Portanto, depois você diz as coisas dentro
Então
do âmbito
eu
do
sou
canal.
formal, dizer bom dia, boa tarde, bem-vindos, gosto muito. Até a próxima.
Vocês estão tão ligados.
Okay, so we will start. I see there's we have to have a mask because we are very close together. So I'm so sorry. Thank you very much for being present here. This is a different symposium of formal methods in architecture, one that has to be done in a time of lockdown or semi-lockdown. So we also had to change lots of things. In May, when we decided to postpone the symposium, we were thinking that maybe in October we could do it live with everyone together. That was not the case. So in fact, we have to have this kind of mixture way of doing the symposium. We will have during these 2 days, we will have a maximum of 10 people here in Isqueté, in Lisbon. And the rest of you, of course, are online. And I hope that everything goes well and we can nevertheless have nice discussions and nice presentations, and we have the time to make these discussions. So we decided to nevertheless have a long presentation, or enable everyone to give a maximum of 15 minutes presentation, and then we will do discussions at the end of the panel. I guess that all of you have been in conferences, these online conferences. We discussed a lot on how to do this. And so we decided to give nevertheless room for more conversations, so that conversations will be more depth in the topics. So I want to also thank David Vian and Franklim, Morais, who are here. Franklim will moderate the first panel, so we will give some words after. I want to thank them for this is the first time that a formal method symposium is done outside Porto. So at this year, Isqueté hosts the symposium. This is the 5th edition. Formal methods in architecture started in 2011 in Porto, and it's a symposium that occurs every 2 years. So we are in the 5th edition. So in 2 years' time, David, Franklim, and George have to decide where to go. So the idea is every 2 years to make it even more international and more broad. Also because this time was very confusing, we had a much more acceptance for the conference than indeed happened at the end. So we then decided to make just a 2-day conference. Several authors gave up on presenting and gave up on doing their papers because they were confronted with these lots of changes in life. So, but we managed to do a nice book, and the book is going to be printed. It's almost published in Springer. I think that all of you already got the chapter to check if there was some inconsistencies. So it will come, I guess, in the next weeks. It's already available to pre-order online, so the book already exists as something, but the chapters are not still available online. So we have these 2 days, we have 29 presentations, we have 5 keynotes, so it's a very interesting, it will be a very interesting, I believe, symposium, several interesting discussions among the authors of the papers and the keynotes also. So I hope that all of you enjoy. We had previously thinking about having workshops as the previous editions, but we then decided that no conditions were here to make this workshop, so we gave up on them. I'm sorry if that caused any inconvenience to you. And I will ask something to all of you, if possible, of course. If possible, make your face visible. That would be really good, because we are not we are not face to face, we don't see each other, and it will be much more nice if we can nevertheless look in the eyes. So me and David now are with the mask just because we are the two of us here, but then every time that someone comes here in Isqueté, we will take the mask out because everyone else will be a bit apart. So trying to minimize a bit this distance that we have among us. It's much more nice when we can nevertheless look in the eyes of everyone and see the expressions. We will have kind of, I think, average 4 authors presenting in each panel. What we thought was that these 4 authors present, and then at the end we have a moment of discussion. Nevertheless, if you want during the conversation to ask a question, we thought that would be nice to use the chat, pose a question, and then we have 2 people here. We have the moderator, and we also have Maria João, which is working as kind of the host, trying to make everyone available. So if you also have some doubts during the how to interact something, you can send a message to the person that is called 5FMA. Okay, so that person is our back office, and she's working to make everything available and working well. I don't know if you have any question regarding this. It's always the same link for the 2 days, so no need of change. Of course, the coffee breaks and the lunch, it will not be a really friendly getting together. We have here some little packs for the people that are here, and we also have a brown bag lunch. And we can also leave the link open, but I think that everyone also wants a break from the online conference, so we will need to have separate coffee breaks and separate lunch time. Okay, so we'll give the word to David. Just
well, hello, good morning to everyone. I would like to start by thanking you all for participating in this symposium. We are not facing easy times, so you being here is really important for us. I also like to thank Isqueté and the Sadilor for welcoming us here this year. As she said, we used to do this symposium in Oporto. This year we are doing here in Lisbon. I hope we will do it again here, but in a better circumstance without a pandemic going on. And that will allow us to be together again. One of the main goals of this symposium is to put people knowing what they are doing, the kind of research they are exploring, and the areas that we can put working together, and the things that we can discuss together instead of looking to these formal methods in a separate way. We like this open space of talking, of dialogue, of clashing ideas, of contrasting perspectives, etc. So this is important for me to say, because one of the things that we try to do in this symposium is to everyone have the ability and the opportunity to talk, to raise questions about the research that is being presented. That's one of the reasons that we always had plenary sessions, not parallel sessions, regarding everyone can see and can learn from what everybody is doing instead of having to choose parallel sessions. So this is important for me to say, because I really would like this, despite of all the circumstances, to be participative and a participated symposium. So we would like to have questions from you, and we, despite this distance between us, we would really like to have dialogue between us, and we will try to contribute to that dialogue, also posing questions, etc., etc. Finally, I'd like to thank Franklim and George Vaz and the remaining organization staff that were incredible doing this. So again, thank you, and hope you enjoyed the symposium. And we'll be here during the next 2 days. So let's have fun. Thank you.
Okay, great. Franklim, you want to start?
Yeah, I'm taking off my mask. Well, we are going to begin with our sessions. We try to organize the sessions so that we could have a good discussion on the themes that you would like to present. Not always possible due to our new configuration, but I think we'll have some good opportunities to develop a debate on our themes that we are going to learn. Well, in this first session, we have 4 presentations, mainly in the area of production, design production of architectural project, with several points of view regarding better to listen to what our authors have to say. I'm going to give the word to, well, sorry, Inês Caetano, I think it's the first one.
Yeah, it's me. Good morning. I'm here.
Okay. Well, the name of the communication is mathematically developing building facades in algorithmic framework. And please proceed. Thank you.
Okay, thank you. Share screen. Good morning, everyone. My name is Inês Caetano, and I'm going to present the paper, Mathematically Developing Building Facades, an Algorithmic Framework. This paper is also authored by António Leitão. The importance of algorithmic design is increasing in architecture due to its advantages for the design practice. This approach is based on algorithms and empowers the creative process by facilitating design changes and the exploration of larger design spaces in viable time. It also supports the search for better performing solutions that satisfy environmental demands by automating repetitive tasks like the evaluation cycle, typical of optimization processes. Still, algorithmic design requires specialized knowledge that most architects do not have, namely programming experience. We therefore need to make algorithmic design more accessible to architects, providing them with ready-to-use algorithms that can be combined in arbitrary ways. To address this, we present a mathematics-based framework for the design of facades. Building facades are the outer layer of buildings, separating the inside from the outside spaces. Therefore, these architectural elements have many associated functions, namely environmental performance, structural behavior, cultural identity, and urban communication. Lately, the design of building facades has become more complex due to the current tendency to create complex patterns and the growing design constraints that it has to deal, namely environmental requirements, economic limitations, tight deadlines, and manufacturing technologies. Due to its flexible nature, algorithmic design helps dealing with these constraints by reducing the time and effort needed to explore different design solutions. Therefore, to facilitate its adoption in architecture, we propose a flexible mathematics-based framework that tames the complexity of algorithmic design techniques in the design of facades. The framework is structured in a 5-folded classification, wherein each group contains several algorithms addressing the different stages of the facade design process, namely design exploration, analysis, optimization, and rationalization. Regarding the follow methodology, this research was based on the idea that sets of algorithms can be generalized and reused to explore new designs. We believe this idea will reduce the time architects spend with the algorithmic task, as it avoids writing algorithms from scratch every time they start a new design while preventing potentially error-prone programming efforts. However, when the predefined algorithms are not well structured, it becomes difficult to combine them. Therefore, besides the different predefined algorithms, the framework organizes them by function while suggesting combination strategies suiting the different design stages. As a result, despite not considering all possible scenarios, the framework addresses the most common ones and can be adapted to more specific ones. To develop the framework, we follow the two-step process. First, we define the mathematical theory for facade design, and then we implemented the theory in a framework containing predefined algorithms that can be combined in arbitrary ways. In both tasks, we had to consider the variability typical of architectural practice, which requires the adoption of different approaches for different projects. And this is true for both algorithmic and non-algorithmic design approaches, but as this investigation addresses the algorithmic one, we must handle variability in a way that the computer understands, namely through programming languages. These are, in most cases, inspired by the universal language of mathematics, and therefore we consider its formalism to structure the algorithmic design theory, to implement the different algorithms, and to organize both in an algorithmic framework specialized in facade design. In the end, we had to guarantee the final framework handles the architectural design variability by adapting to the ever-changing design requirements, diversity by embracing and evaluating diverse design problems and scenarios, and coherency by correctly integrating the design information in a single workflow. We believe the resulting framework will promote the use of algorithmic design in facade design, solve the interoperability issues between design and analysis tools, and guide the selection of the algorithms and strategies that best suit a design scenario. Regarding its structure, the framework organizes the algorithms based on their type and role in the facade design process in the following groups: geometry, distribution, pattern, optimization, and rationalization. For each one, it provides algorithms that can be then combined with one another through function composition. The first group contains algorithms to define the facade geometry. These are often two-dimensional, varying in the U and V dimensions. As an example, to parametrically represent a planar surface, we have the straight algorithm, which, based on a width and a height, creates the parametric description of the facade surface. In the paper, we describe in detail the mathematical representation of the algorithms of this group. Regarding the distribution group, it contains algorithms to distribute elements on a surface. These receive a matrix of the surface points on which the distribution will be made, which are provided by the geometry algorithms. They then return another matrix with the same points rearranged in different distribution configurations. This example illustrates the grid square algorithm, which rearranges the points in sets of 4 points describing a squared area on the surface. But there are more algorithms available. This example illustrates, for example, the grid rhombus algorithm, which rearranges the points in sets of 4 points, but describing a rhombus-shaped area. And this algorithm, the grid hexagons, reorganize the points in sets of 6 points representing hexagonal areas. In the paper, we describe the available distribution algorithms in more detail. The pattern group contains algorithms to create different geometric patterns. A geometric pattern often results from repeating an element, either along 1 or 2 dimensions of a two-dimensional domain. In both cases, the repeated element can be kept unchanged along the domain, or can suffer some transformation regarding its shape, size, among others. Therefore, this group provides algorithms to generate different geometric shapes, like circles, triangles, squares, and other more complex shapes, as well as to apply different geometric transformations to them, like rotating, scaling, among others. The optimization group contains algorithms to analyze and optimize the designs, which help users driving the changes made to the geometric pattern. It contains algorithms to optimize natural daylight illumination, to improve the natural ventilation of the building, among other algorithms. The last group contains algorithms to rationalize the designs. These help users controlling the number of different shapes composing the pattern, which is important to minimize the design manufacturing costs while increasing its construction viability. It also provides algorithms to identify and count the different existing shapes that compose the facade design, providing users with each shape typology location and quantities, and information that is critical to proceed to the ensuing manufacturing stage. Here we present an example to explain the framework implementation and the algorithms combination. If we select the straight algorithm, we obtain the parametric description of a planar surface. Then, if we want to rearrange the points describing the planar surface, we can select, for instance, the grid rhombus algorithm and obtain the surface points rearranged in the rhombus mesh. Finally, to create a pattern based on star elements, we can select the shape star algorithm, which creates star-shaped elements. Regarding the shape star algorithm, it receives as inputs the point where to center the star, the number of vertices of the star, the inner radius size, the outer radius size, and an angle. Despite being mathematics-based, the available algorithms can be also implemented in a visual programming language like Grasshopper, resulting in components like this one, which in this case represents the shape star algorithm. By combining this algorithm with the previous ones, straight and grid rhombus, we obtain a pattern like the one you see in the image. And in this case, we are using 6 for the number of vertices. If we apply a scale transformation to decrease the size of both inner and outer radii in the U direction, we obtain a pattern like this. If we apply a different scale transformation to randomly change the size of both radii, we obtain a pattern like this one. And following this logic, we can obtain several patterns. In these examples, we used both shape algorithms, the shape star and shape rosette, with different transformations. In the paper, we detail several of the available shape algorithms. Here we can see some of them, namely the circle, regular polygon, rosette, among others, and transformation algorithms. The latter includes the affine transformations, which we exemplify here with a simple example based on squared elements to which we apply a rotate transformation. Then we add a scale transformation, and finally a translation. Note the transformations here were randomly controlled, but there are other ways to control the geometric transformations. This group also includes other types of transformations, namely rule-based transformations, which result from the application of geometric rules to the patterns. These include shape substitution rules, and as you can see, some of the squares were replaced with circles by following a certain logic. Our color application rules, in this case, the element's color change according also to a rule. Edge deformation rules, which is visible in the top examples, where different rules were applied to a squared grid, and recursive rules, as illustrated in the bottom examples, among other possibilities. To evaluate the proposed algorithmic design framework, we assessed its application in an algorithmic design contest by implementing it in Capri, a text-based tool tailored for architectural design that is based on the Julia programming language and is portable between several design tools, including Rhinoceros, AutoCAD, Revit, Robot, among others. Although we evaluated the framework on a particular tool and with a specific programming language, it can be used in any other algorithmic tool with its own programming language, because the proposed theory is described mathematically and thus it is universally understood. As the framework is algorithmic based, it allows a transition from a manual design process to a fully automated one that is flexible and parametric and thus facilitates design changes and the generation of more complex designs. It also enables the exploration of wider design spaces and allows for the automation of optimization processes. In contrast, manually interacting with the design tool is a non-automated process that requires considerable time and effort to change the designs. This therefore limits the complexity of the obtained solutions, narrows the design space explored, and hardly supports optimization processes. Also, the proposed framework is highly configurable, allowing the available algorithms to receive functions as inputs. It also embraces all design stages in a single and continuous workflow, enabling the modifications made to one algorithm to automatically propagate to the others. And it can become portable between different design tools when implemented in a tool like Capri. There are already some tools that provide functionality similar to those available in the framework. These include ParaCloud Gem and some plugins for Grasshopper and Dynamo, including paneling tools that contain surface paneling functionality supporting grid manipulation and the morphing of patterns and rationalization techniques for analysis and fabrication. Lunchbox that provides functionalities to explore mathematical shapes, surface paneling, and wire structures. Weaverbird that includes mesh subdivision and transformation operators and functionalities to help the preparation of meshes for fabrication. Architect has functionalities to generate algorithmic patterns resulting from tilings, geometric shapes, and grid subdivisions, and added deformations. Scheme Designer that provides functionalities to generate facade geometries from building massing surfaces and repeating panels. However, these tools are limited by the available predefined operators, which often do not respond to more specific design problems. Also, they require direct interaction with the tool, limiting the automation of the design process. Finally, most of these tools resort to visual programming languages, which hardly scale to complex problems. Our framework overcomes these shortcomings because it structures and provides algorithms that adapt to multiple design scenarios, as well as to different design tools and workflows. It motivates an entirely algorithmic use of the functionalities available, but also allows user interaction with the design tool, namely using visual inputs. And finally, because it is designed for textual programming languages, it benefits from the expressive power. Still, in its current state, the framework requires more programming experience than these tools, and is less visually attractive and intuitive. Future work will focus on improving these shortcomings. We have successfully applied this framework in the development of several case studies where we developed different facade designs. We use the framework to geometrically explore different patterns. Here represent some of the examples developed, as well as to analyze and optimize some of the solutions, as you can see in this example. We also use the framework to rationalize some of the solutions, and in this example, we used some algorithms to identify the different typologies of elements used in the final facades, which are displayed in different colors on the left, and as well as to count them, which is visible in the table on the right side. To conclude this presentation, algorithmic design is a design approach that supports the exploration of more complex designs and wider design spaces, as well as to search for better performing solutions. Unfortunately, architects still face several limitations when using algorithmic design, namely the transition from a purely visual to a more abstract design process and the need for specialized knowledge, including programming experience. To make algorithmic design more accessible to the architectural community, we propose a mathematics-based framework to tame the complexity of algorithmic design techniques. We focus on building facades with a major role in building design, and we demonstrated the framework's ability to be generalized and to be applied in different design contexts and workflows. With this, I conclude this presentation. Thank you very much for your attention.
Oh, sorry. Well, thank you for your presentation. And now, please, Ekin Ünlü, I think this is your name. If not, please correct me. Your presentation has the title, Design to Experiment, Experiment to Design. And, well, better listen to you. Please, thank you.
Thank you. Can you hear me?
Yes.
Okay. Firstly, what's this paper about? And we present a curriculum with 3 experimental modules in the field of digital modeling. And we discuss the reflection of the module on students' learning process. And we have start point for the theoretical consideration of this study. It was the constructivist learning theory. And we had questions. The learning the tool and its functions requires more time and attention in comparing to learning CAD/CAM tools in a design context. Learning how to use a tool doesn't always mean one can implement the tool in the design process in a creative way. Therefore, connect the learning and design process to seek a way becomes so much critical. The aim of the course, improving students' 3D modeling experiments with CAD tools, exploring different possibilities, and gaining knowledge towards integrating different media and tools and workflow. And the study aim is to reveal potential connection between observed physical experiments and the design process. Our timeline, it was actually we just analyzed just 7 weeks, and it was until the midterm. It was so long course, and we work with 24 graduated students from this course. It was becoming 3 main modules. Namely tool user, breaker, and designer. What is the design tool experiment? We had talking about that. It's meaning for our digital modeling course process. The course process, which is an experimental study, it's designed with inputs that trigger the thinking mode that comes out when designing. The education process designed with, I said before, constructivist theory, that approach learning by doing and learning by discovery. They are coming from, and we refer also to Facades. And this figure is coming from Hofstad's chunking idea. In this context, weekly tasks are defined in consideration of the chunk-based modular structure. And the tasks are expected to involve links with the other task. And we give the task and students reflect their own observations. We call that internal relation. And we also give different physical and chemical experiments students did, and we also call that external relation. What is tool user, breaker, and designer? And tool user first three with names. In this phase, students are encouraged to use digital modeling and fabrication tool. Tool breaker is students are encouraged to develop their own experiment setup. It was physical and chemical process are expected to cover some following key concepts. They did document the observed process. They made diagrams and analyze, and they develop bottom-up rule-based strategy for digital environment. Tool designer is students are expected to adapt their previously generated from making strategies to given a context. What about experimental design? It's meaning an experiment digital modeling course of process. And first week, students are asked model the lost, missing, broken parts and object in their school, in their campuses. They made with 3D printer. After that, after 2 weeks, they rescale their previous model, and they rescale 3 times, and they reproduced. They use different techniques and molds. During the following 2 weeks, exploratory material testing task based on process research. And last 2 weeks, students were expected adapt their growth prosody algorithm to a spatial context. And tool designer student task includes digitalization, digital model optimization, and algorithmic definition. And we have not one focal point, we have so much focal point with that task. And I want to show some students' work. And sometimes students forget algorithm, they just focus suddenly they started to thinking growing and prosody and material. Some of the students scared explore because they thought modeling will be hard and they hadn't experience with that. Because we want also from the students algorithmic rules. It was our process last semester. And I want to show much more detail. It's the first one. We was the teaching some fabrication tools and digital modeling. And the second one, it was again experiment and tool design and part. It was mixed type. The conclusion, the effect of the learning experiences in design process was achieved by comparing the result each task and present in this figure. We try to compare I want to show again. Digital techniques in design not only change our design presentation. We want to show that idea our students, but also create new reasons for design thinking. The tool user breaker course setup created in this context supports the digital modeling process with experiments. It has the potential to encounter changing and transforming material behaviors with experiments to discover physical events using digital modeling and analog computational models. Thanks to our students and research assistant. Thanks for my teacher for our paper. Thanks for listening, everyone.
Okay, thank you. Well, next presentation from Shotet Sikolia. I think it's the name.
Yes, hello.
Okay.
Hello, thank you. I'm going to share my screen. One moment.
The title for the presentation is Tectonics of Differential Growth, Folds in Additive Fabrication and Molding for Architectural Design.
Right. Do you see my screen? Yes, thanks. Hello. I'm going to talk about the project which actually has started as a student project in which we seen some potential, so we thought to develop it further. Differential growth is process of volumetric expansion with a spatially uneven speed and intensity, which results in appearance of folds. We can see it in many places in nature. Particularly, it's often seen in the surfaces in nature in epithelial structure. Looking into the differential growth, at first we looked at particularly popular project which I think many architects have seen recently, research by biologists from Spain on the development of faults in the epithelia through the development of geometrical shape described by these researchers as scutoids. And we thought that this geometrical approach is slightly different from previous attempts on generating differential growth or simulating differential growth, and worth trying out. If we look at the architectural precedents, there are many ones which I would like to particularly highlight are design objects by nervous systems, then several projects by Neri Oxman, who uses differential growth to differentiate mechanical properties of the structure, but also projects of Alice Andrasek within RMIT or before in London, which differentiate across multiple resolutions using the differential growth algorithms. If we look on the technical side of this process, then it was originally well described in a paper by Andy Lomas, who described one of the ways, one of the possibilities of simulating differential growth using digital technology. And recently, in relation to the research on scutoids by the biological research which I mentioned before, there was quite interesting paper by Subramanian and his group, which was not concerned with differential growth per se, but which was concerned with modeling of scutoids and paneling of scutoids by lofting several Voronoi divisions through each other, the process which was by the author described as Delaunay lofts. So we tried to kind of stand on these precedents and proceed. We started quite simply by kind of mechanically repeating the process described in the paper on the scutoids in epithelia. The first geometric approximation which we did consisted of two offset surfaces. Both of them were divided or at first populated with random points right above each other, and then according to this random points divided through Voronoi diagram. The Voronoi diagrams were lofted, and that would create prisms because the Voronoi cells are exactly identical since the surfaces are identical. Then we would add or insert randomly several additional points on one or another surface and proceed with lofting. And this time, since Voronoi surfaces were not identical, the prisms were supplemented with other shapes, whether that being pyramids or that being scutoids as described previously. While we applied a spring engine, I think at this point it was Kangaroo, later we used some custom-made spring engine, iteratively to this structure, faults would start to appear. As you see here on this image, these are just screenshots of several iterations. Faults which are not unlike the ones which could appear in the epithelia. The problem with this approach was it was computationally very heavy. There was lots of redundant calculations going on. And also, since from the beginning, our research was aimed at the fabrication of differential growth structures or faults realized through differential growth simulation. And in nature, materialization and shape are inherently connected, things getting shaped while they're getting materialized. While in our case, simulation and fabrication are separated, so we can simulate some shapes which we cannot fabricate later. And this approach would often lead to such shapes. So we tried to try a kind of second approximation, second geometrical model approximation, which would be simpler computationally and more related to our to the fabrication method we had in mind. And that was instead of using originally 2 offsetted surfaces, we would use 2 offsetted curves, subdivide them, and then insert on one or another side additional points, and then proceed with iterations of the spring engine. So basically, if we consider this approach 3D, that would be 2D, obviously computationally much faster. In our idea, we planned to use FDM 3D printing of the mold, which would be later filled with liquid material, whether that is epoxy or concrete. And since we use traditional 3D printers, not robotic arms, which kind of print layer by layer, the use of 2D approach, 2D lines, which could be later stacked above each other and give us a G-code, was particularly fitting. Differential growth, of course, is interesting because the control resides in a level lower than in which it is expressed. So the form, the character of the form is non-determined. You can't really pre-design it. Yet we needed some tools of some sort of top-down control, while in detail it would be kind of bottom-up, but some tools of top-down control. And these tools were 2. One is we used constraints. As you see here, the curves start to grow. As they grow, we are moving them up. So the kind of timeline or time arrow is now is an arrow Z as well. And but they cannot intersect the given constraint, in this case, the red surface. And another way of controlling it was simply picking up a basic curve which was supposed to grow further. So we called it a footprint. You can see some tests and elements here on this diagram when a triangle on top leads to this kind of structure, a rhomb leads to this kind, etc., etc. Later, we used also more complicated footprints. At first, before we proceeded to fabrication, we just tested different kinds of applications to different typologies, from the scale of interior elements of furniture to the scale of houses. What was particularly interesting or worth mentioning for us was the kind of automatically appearing typology of a mushroom or mushroom-shaped typology, which we thought could be in the future interesting to test as a kind of in architectural scale. Another interesting thing with the mushroom-shaped typology is that whenever 2 or 3 simulations of differential growth would happen at the same time, this growing mushrooms would act as constraints to each other, meeting together and creating some sort of vaults. So the architectural language or potential for architectural language, we thought, was quite promising and quite rich. Eventually, we had to proceed to fabrication. The fabrication method which we chosen, as I said, was 3D printed molds. However, the trick was to combine high resolution, which we wanted to achieve, and reasonable speed. We wanted to avoid very kind of thick filament printing, which is rather fast. We wanted to achieve a higher resolution and smoother surfaces, so we would proceed with resolution typical for 3D printing with nozzles around 0.5 or 0.6 millimeters thick. However, in order for the 3D print to be reasonably fast, the shells of the mold had to be incredibly thin, basically 1 layer thickness. Obviously, such mold cannot hold the weight of the material inside of it on its own, whether it's epoxy or concrete. So we would fill the space inside with the concrete at the same time as we fill the space outside with sand, which is approximately of the same weight. So achieving an equilibrium between the pressure from inside and from the outside. Later on, of course, when the concrete solidified, the sand could be taken out and recycled. Therefore, the only thing in this approach which is not recycled is this kind of thin layer of plastic, which volume-wise or mass-wise is negligible, therefore achieving relatively efficient or relatively sustainable process, the non-recyclable bit being just a small part of the whole structure. As I mentioned, the use of very thin shells allowed us to go very high with resolution, so the resulting surfaces are pretty high in detail. Eventually, we stick up to expanding fiber reinforced concrete as main construction material because the expansion is advantageous in filling the small deformations of the mold, adding to the detail which we can approach. The use of concrete seemed adventurous to us, also because, well, we know a lot about this material and we don't know that much about the geometry. So as further research, we plan to do more structural analysis of this kind of shapes, and it's good to have at least some parts of the research kind of more defined, in this case, the material, since the geometrical qualities are yet to be explored further. Besides the kind of structural research, we found very interesting the fact that basically this approach allows to maximize surface in relation to the volume, which could be very advantageous in heat dissipation. In particular, right now we are proceeding with development of this research in applying the concept of in applying this kind of simulation, this kind of geometry to urban surfaces, which of course have immense effect on the urban heat. For that development, which is going in process, is not quite finalized, we use actually the original more computationally heavy 3D approach, which I described first, with offsetted surfaces rather than offsetted curves. And first tests seem quite promising, with difference between in urban elements left outside between the flat bits and bits deformed by differential growth, the temperature difference being of several degrees. However, I would still like to look at it further on. Thank you. I believe that's it.
Okay, thank you. Well, the first three presentations have many points in common. Now, this next presentation will be rather different. The title for the presentation is Agent-Based Semiology, Optimizing Office Occupation Patterns with Agent-Based Simulation. Well, I'm going to Robert Neumayr. I think it's the right pronunciation.
Yes, thank you very much. You already, thanks for the introduction. That's exactly what I wanted to say about the presentation. We are venturing a bit into a different territory right now. I'm gonna try to share my screen and see if that works. So, can everybody see this?
Okay.
Excellent. Okay. we are going to be much less geometric, but a little bit more looking into social interactions. The title of our research is Agent-Based Semiology, and this paper will deal with the question of optimizing office occupation patterns with agent-based simulations. So just very briefly, what are we trying to do? We are trying to investigate, simulate, and optimize spatial occupation patterns in contemporary office environments in order to understand the performance criteria that link these spaces and the users in it. Why are we doing this? We have the ambition to develop a method of architectural design that allows us to generate environments with a high social performativity and that can be optimized for the specific patterns of use. And then how are we doing this? Essentially, we're embedding our research in the conceptual framework of agent-based simulation. And this means that in our research, we're not foregrounding the configuration of space itself, like other tools that look into the performativity of spaces too, such as space syntax maybe, but we are focusing on finding behavioral rules of social interactions for a set of agents within that space and try to develop a population of agents that is sophisticated enough to allow for the emergence of plausible lifelike event scenarios. And then we are simulating these and evaluating the results of these simulations. The question of the performativity of office spaces is a very long-standing research, and I think it's safe to say that office spaces have changed a lot since they first came up in the mid of the 19th century, and they changed because the complexity and the way the nature of work evolved during these times. In the very beginning of office space layout, offices were essentially organized in a very linear way, meaning that you handed one thing from one to the other, and it was quite simple to evaluate the specific office layout because you would essentially just, at the end of the day, count the number of papers that were actually written or the number of units assembled, etc. Over the time, obviously, the way that people work together became a bit more complex and intricate, and this is how the layouts changed.
Sorry, something happened to your presentation. Well, I think you. Okay.
Something happened.
Sorry, you must begin.
All right, can everybody hear me?
You have to, yes, we can hear. You have to resume your presentation.
Okay, at what point? Okay. All right, wait. Can everybody see the screen?
No, not yet.
Okay. Okay.
Okay.
All right, sorry for that. I don't really
Not
know
where you left it.
So I think this is where I left, right?
Yes. Yes.
Okay, sorry about that. I was just trying to explain that the office layouts have changed over time and became more complex due to the way that people started interacting, and in the same way the methods of evaluation did change. For these kind of office spaces that we all know very well, the most successful way of simulation is using space syntax. However, with the arrival of knowledge economy, another change occurred quite recently, because in one way or the other, the nature of work changed from the exchange of goods or materials to a constant exchange of information and knowledge. So essentially, work patterns changed again. And there's a lot of research shows that a lot of new different working patterns have evolved in the last couple of years that range from the very low mobility kind of work patterns that we were used to towards very complex and very dynamic patterns of office space use. It's therefore the hypothesis of this research that in this dynamic environment, if we want to evaluate office space layouts, we can no longer look at the morphology of the space itself, but we need to look at the interaction of the agents within it, because by the way they move and interact constantly, they start to show unpredictable and emergent configurations that need to be understood as a result of the actions themselves rather than as a result of the space configuration. Therefore, we decided to move into agent-based simulation to simulate this. Agent-based simulation or an agent-based model, quite simply, is a computational model where you look at the interactions of autonomous agents, but with a general view to assess the effects on the system as a whole. So the assumption is that the addition of the small interactions, in essence, create a general layout that we cannot predict, but that we can essentially simulate and evaluate. That's not exactly a brand new idea. The first agent-based system famously was done by Greg Reynolds, and it was called Boids. It was done in 1987. And it was looking into the interaction of flocks of birds in the sky. And he was able to create a multitude of different configurations just by focusing on three different properties that these birds or agents would have. One would be the property of cohesion alignment. So you would essentially follow the majority of the birds. The second one would be separation. So you would essentially stay clear of becoming or getting too close to your neighboring bird. And the third thing would be you would essentially evaluate whether you need to change your course in order not to bump into a fellow bird. These kind of logics operate on all kinds of, let's say, groups or formations, flocks and schools of whatever, where a lot of different individuals form in different groups and depending on the different spatial environments. So here you see the same type of animal being arranged in totally different formations depending on what they're just about to do and what the actual environment would be. Of course, it's safe to say that office interaction is a bit more complex than that. So what we were doing, we were trying to look into more sophisticated agent models. Agent models can be broken down in three different, let's say, submodels. The agent model, that's essentially dealing with the question of how an agent interacts with the environment, would essentially be collision detection and avoidance, simple visions, stamina, etc. And there would be the social model that I'll be talking about in a second, which essentially deals with the question of how agents interact with other agents. And there would be the behavioral model where you essentially talk about how the behaviors and the desires and wishes of different agents are being stacked and processed within the simulation. Like all these different types of behavioral models have been structured from quite simple to quite sophisticated. And we're trying to work through them at the moment. The elements that you see that have a red frame are the ones that we are working with. The other ones have not been achieved yet. For the social model, we decided to focus on two key questions. One question would be who talks to whom within a space or within a group of people. We call this parameter social attractiveness. And the other question is for how long would that conversation be going on? We call this variable social alignment. Essentially, social attractiveness for us is essentially something like a container that would contain all the properties of an agent that would make him more or less desirable to talk with. So I'm not talking about the physical attractiveness of a person, although that might be part of the calculation, but I'm also talking about that agent's position in a company hierarchy, for example, or that the person's knowledge or information about specific topics that he might have that you would want to talk to him because of that. Talking about the social status and all these kind of things. So all these things and many more can be taken into consideration and need to be formalized in order to have a value that then can be processed. The social alignment essentially stands for all sort of properties that make you want to talk to somebody for longer or shorter, which is like common interests, maybe personality, a nice person, not a nice person, member of the same team, member of the same floor, working in the same project, familiarity, you already know him, etc. So that would essentially define the duration of the conversation. And with these two parameters, you can essentially start to set up very simple agent models. Obviously, there is restrictions to the way that agents interact with each other. One is the physical range, which essentially means if somebody is too far away or is not visible, is around the corner, you will not be able to talk to this person. The other one that we're introducing is something like a social range, which precludes interactions with within different agents that have whose social status is too different, which is essentially a reflection on what can be seen or experienced in normal conversations. So if you browse through different cultures, so in different cultures, there's different types of hierarchies and different types of respect. So somebody very low in the hierarchy would not be able to talk to somebody who's very high in the hierarchy. So these two ranges we introduce and we can play with them in order to try to find a suitable setup. And as it turns out, that just by using these two ranges, you can create all kinds of different circulation and conversation patterns within one and the same space. So for example, if you have a very high physical range and a very high social range, you have a lot of conversations and also a lot of traveling, because almost every agent is eligible for conversation. If you have a very low physical range and a very high social range, you would get a similar result, but you would have people talking to almost everyone, but in a very close space. You would get these super clustered kind of types of conversation patterns. The other thing that we were introducing, we were starting to treat objects such as tables, conference tables, coffee bars, etc., in a very similar way, also assigning attractiveness to them. Obviously, that would not be some sort of personal thing, but for example, a high table would be very attractive. It would be in the center of the room rather than next to the exit and things like this. So all agents can be treated in a similar way. And again, by playing with the physical and social ranges of these agents, you can achieve totally different conversation patterns within the space. In order to get the research started, we were organizing the research in the kind of chart where we would, from the top to the bottom, step by step increase the complexity of the different agents, starting from very, very simple agents that would just be able to acknowledge their simulation environment, such as walls, columns, etc., to the bottom where we have implemented all the social simulation things that I've been talking about. And on the lateral, so this would be this sort of line in the kind of horizontal line, we would be testing the same kind of setup on a lot of different configurations in order to find out whether there's a consistency within the simulation or there are outliers, etc. I will just briefly show what these simulations actually look like once they run. So this would be like a typical setup in a simulation space. We're always using the same simulation space, which is modeled according to an office space in London, with the idea that at some point these things could be tested against actual measurements that were taken in that space. So you see that while you see this simulation, then we can extract all the information that's delivered from there. So we know exactly at what point people have what location, who they meet, where they meet them, for how long this conversation goes on, etc. So as a preliminary result, essentially what we can find out is that the simulations show an overall lifelike behavior, and that the agents show differentiated behavior towards other agents, but also towards the architectural layout within that space, and that different space layouts result in differentiated spatial occupations. If we know this, then we can essentially start to try to evaluate different space layouts. This is what we were doing in the next step. So you essentially come up with a number of feasible layouts that you would devise if you would be an architect and just run the simulation across them. And then you just look at the performance values and see what's the overall number of conversations, how many conversations at tables, at high tables happened, how many at low tables, coffee bars, etc., how many free floating conversations in the space happened. And this is one of the results. It's interesting to see that the total number of conversations are pretty stable. So there's no significant variation within them. But however, how they're distributed across the different objects in the space is highly changes a lot. So you see in this table, you see green is always the highest number within the simulation set, and red is always the lowest number. So, excuse me. So it seems that we are able to tell a good configuration from another, or from a bad configuration within a given set that we have devised. But what we can not really do is we cannot really say with confidence that we have found the best solution for the furniture distribution in that space, because we might essentially be missing something which is totally different and we haven't come up with, because normally we design from intuition, and we might be essentially trapped in something that I would call like a local peak in the fitness landscape. So if you imagine all the possible configurations within that space on the X and Y plane, and the fitness, or let's say the performativity of these configurations in the Z axis, then you would essentially, from your intuition in a normal design process, devise a layout, test this, and then you might be where you are. You might be here, for example. Then you would try to improve it. So you would change the configuration, and if you change it the right way, you would essentially climb up this hill to a local optimum. But what you do not know is you do not know if there's a kind of much higher peak somewhere else, where you would only get towards by going through a kind of valley, right? So in order to be able to do that, I think we need to look into a different strategy. So we need to move away from that sort of analytical tool and try to get something like a generative tool. And for this, we're looking into strategies that come from genetic design strategies. So essentially, it would be great if we could sort of distribute a seed of random different configurations across the fitness landscape, and then just test all of them automatically for their performance. And the algorithm will help us do that. So essentially, the idea is to seed a huge number. In this case, it's 100 different variations of office configuration, and just produce them randomly and arbitrarily in order to avoid that sort of designer's bias of something that might already have worked, and then test all of them for their performance. And this is just a quick cycle through all the random configurations that we tested. And all these configurations result in different occupation patterns, which you can see here. And then of course, you need to remove all these configurations that make little sense. For example, if tables are on top of each other, or if tables are within the walls, because we haven't really precluded them in the first step of the design process. And I'm just showing now, evaluating all hundreds of these, and I'm just showing now the, let's say, the three worst configurations. So we're looking for any kind of peak performance. In this specific case, we look for the highest number of free conversations in the space. And I'm showing the three worst scenarios, where you see that the number of free conversations ranges somewhere between 70 and 73. And it's interesting that you see that there is a specific, you can extract specific generalized patterns from this. So you can essentially say that all of these have a table somewhere in the middle. And you can then compare that to the three most successful variations, where you see that the number of free conversations is essentially between 81 and 97. So there is a significant increase in that number. And you can then again look at the patterns and deduct that apparently the tables in these cases are much wider distributed. So they move to the edge of the space. And that obviously leads to the possibility of let's say, making assumptions and saying, for example, our assumption would be that if tables are distributed that way, that they just leave enough space in the middle for these kind of informal conversations that we're looking at.
Robert, I would like you to get a little, well, if you can finish.
It's the last slide.
Okay, thank you.
Sorry, yeah. Just a very quick discussion and outlook. Using this kind of system, I think it is able for us to tell more efficient layouts from less efficient layouts. But essentially, I think the key question here is that at this time we need to say that the question of realism of the entire simulation is a bit difficult to answer, and we need to do more experimental investigations into that, as well as we are trying to calibrate the simulation with the real life observations that can be made in that specific space that we were simulating. But essentially, I think, and that's for us the most interesting aspect of this, I think that in order to make comparisons between more and less effective spaces, the exact measurements and numbers are not necessarily the most important thing. I think that the notion that one spatial organization seems to have advantages in performativity against other ones, and that these can be described in the simulation are, although they might be a bit imprecise, a very interesting and valid first step for the further investigations that we're doing. Okay, thank you.
Thank you. Well, now we will have, and congratulations, we are almost in schedule. We have, I say half an hour to discuss what we just heard. And well, if I think if you want to say something, please raise your hand. Is it okay? Yes. You can see Maria João, you can see who raised the hand. Okay. Who wants to make some question, say something, please raise your hand. And Maria João, okay. Sarah?
Okay, so I don't know if everyone can listen to me. Maybe not. So. I'm going to stand up next to the microphone then. Can you listen? Yeah, I guess so. Yes. So, yeah, thank you very much for the presentations. They were really nice. I have 3 questions for 3 different presenters. Maybe I will, Frankly, what should I do? Pose all of the questions or one at a time? Okay, I'll do one at a time. Maybe it's easier. So I would like to ask Inês, Caetano. I like very much the presentation. And I was wondering if there is a relation between the facade and the interior layout of the building. So for instance, when you mentioned the optimization of the sun energy, there are rules in the regulations regarding the window size and the interior size of the room. So is there any relation between the facade and the interior? That's the question for you.
Yes, because how can I explain? To have a better performance in the inside spaces, we have to consider what they are, their functions. So this is considered in the framework, because otherwise we were optimizing an abstract space that have no function. So yes, it is connected.
Sarah?
Okay, great. And I would also like to ask, I would like to ask, I'm sorry, my clock. I would like to ask Robert. I liked it very much, the presentation and the possibilities of the tools that you presented, this agent-based semiology. I think I understood well that you were talking about levels of conversation, wasn't it? My question is, how did you got the data from the levels of conversation to feed the system? So you said that in high tables and low tables, so you showed also a slide with several layouts, different configurations for the same space where tables are positioned in different ways. How can you have the data to know if people will speak more if the table is, I don't know, next to a window or in the specific corner or in the other? Yeah, so where is the data to feed the system?
Yes, that's essentially correct. The system works like this. So essentially, we are not collecting this data. We are trying to produce this data in a way. So what we are collecting is information about the social interaction, meaning that we make assumptions at this point of how people would communicate with each other. And for this, we have these two values introduced, and we have certain ranges that preclude specific interactions. And as a result of these interactions, people will approach each other, or people will essentially approach specific objects in the space, for example, within their range, right? So very simply speaking, so you would essentially have a table in an empty space, or you would have two tables in an empty space, and these tables would have different, let's say, attractivenesses in a way, because one would be next, I don't know, to the toilet, excuse me, and one would be in the middle of the space. So the first person who would enter would essentially go to the more attractive table. So the next person who would enter would then scan the space, and the attractivenesses of the table and the person at the table would be added together. So for example, an attractive table and an attractive person would make a very attractive package, right? For you to go there, a very attractive, well, let's say a very unattractive person at a very attractive table would lower the overall quality of that package, right? And depending on this, you would then access maybe a different table or maybe that table, and that whole thing sort of keeps on spinning, you know, and keeps on going until everybody's in the space, and then conversations would end because the duration is over. Then people would again start looking at the nearest person with the highest attractiveness and so on. And this is how the configurations change and continue and reform during that simulation, right? So and by that you can then essentially find out which configurations are more successful. But first you need to establish a sort of success criteria, right? So you need to say, and that was our assumption. So there's a lot of research that indicates that in knowledge economy offices, it's very much about informal conversations, for example. So it's very important that you meet people, I don't know, in the kitchen or on the corridor, on the staircase, in order to exchange information. So what we were looking here for is these kind of informal free-floating conversations where you would not schedule meetings, but you would meet somebody in the space and start a short conversation. So we were trying to get peak performances for this, but in the same way you could look for peak performances at conference tables or low tables or etc. And then different configurations would give you different values for the interactions with these objects, and this is what you can evaluate. In the first step, the different layouts are sort of, let's say, educated guesses, right? So which would be a sort of architect's approach, right? So if somebody tells you, I have this office space and I want it furnished, then you would sort of start thinking, okay, where would the high table go? Where would the coffee bar go? Where would the conference table go, etc., right? And there's only a limited number of meaningful configurations for any given space. and these you can devise, and then you can test these, you know. But then in the second step, and this is what I was showing in the end, you can essentially say, maybe I've overlooked something. So there might be a configuration that's even more efficient, but I haven't come up with it because it's maybe counterintuitive or something like this. And these are the ones that you will not be able to find when you design intuitively, but these are the ones that might be found if you start with a random configuration. So this tool might essentially help you to venture into that space. Obviously, the first choice is always to go by intuition, because that's what architects do, right? We have a lot of experience in doing that. So, and from this experience, we draw for the design of spaces.
Can I add something besides your, or complement my question? Besides your intuition and these assumptions that you do on how people talk, did you find something in literature, mainly coming from psychology, on the topic? Because usually we use data that was already tested by someone else to feed these systems. So in a statistically way, using intuition on using your assumptions doesn't represent much.
I'm not, maybe that's a misunderstanding. I'm not using intuition to define my social system. I'm using intuition on the layouts that I'm testing, right? Okay, sorry, that maybe I wasn't really clear on that, right? We started essentially with random numbers in order to test the system, and for the way that we are trying to define what we call attractiveness of the people, right? We're looking into things like social network analysis and something like this. So within a company, there's different ways of finding out let's say how attractive or how important people are within that specific office framework. For example, by analyzing email correspondences and something like this, right? So you can come up with specific networks where you see who is in the center of these, who has how many connections with other office employees, who is doing a lot of let's say information translation, and who is rather at the ends, right, of that kind of network. And these are informations that can then be used in order to look in or to assign attractivenesses to the different people.
Robert, to complement this, sorry, Sarah, for the last question. Well, you surround the agents in the space and they act, well, with their rules, their theoretical rules. The question is, have you some empiric data that can support that the theoretical model of the agent is, well, it equals the real behavior of real people? You have empirical data to support that?
No, we're looking into comparing the results of what we've been simulating to data that's been taken in that space, actually. So that space that we modeled exists, and it's furnished like this, and data is or was about to be extracted from this space before everything went into home office. So that will be the next step, to look into comparison of the simulation that we have with what's actually going on in that breakout space in that office in London, and then try to see differences or things that we have in common, and try to hone and make the simulation better. So the answer is, at this point, we do not have that. That will be the next step.
Okay, thank you. Sarah, you had another question?
I know, but probably someone else wants to pose a question.
Well, someone else?
Yeah, I have a question to Ekin about your presentation. You said the students had the opportunity to try different tools. My question is on an issue that we sometimes discussed here in the Formal Method Symposium. It's about the problem-solving approach. So my question is, how do students approach those different tools? They do it by trying to understand what kind of way and what kind of tools they will have to explore in order to solve the problem they have? Or is there a sort of a pre-established methodology that will go through evolving different tools? So the first one is a more empirical approach that they will try to explore the potentiality and the limitations of the tools regarding the problem they have to solve. And the other way is a structured way where you put a kind of a method, if you want, and they go through that method, understanding where the tool is needed and when and doing what. So this is my question.
Sorry, I didn't understand last sentences.
Which part of it?
The last.
And yeah, first part, I thought you are talking about the tool tool breaker, or which part is the first part teaching the fabrication tools. They are students meeting that tools, and they are exploring the digital tools and with the CAD and CAM tools. But the second part becoming the suddenly we stopped using the tools. They are starting to experiment and with the keywords, and that was just the discovery.
Okay, so it's a kind of a mixed approach between a structured one and an empirical one, right? Yes, at the last part, we want to one scenario with the architectural design. It just be just the space, but we need the scenario. What is the story? It can be space, and it can be on the earth, but we need just place. They have to modeling to and for the living space. That was just one thing we want. And otherwise, and they mix last part. They mix in the first experience. They meet CAD/CAM tools after they did experiments. Last part, they mixing everything with the architectural space. It was conceptual, actually, last part. Okay. Okay. I hope I could answer. Thank you.
Well, I have a question with an hard one. Well, the first presentations present some grammars, parametric grammars to produce objects. Well, the presentation from Robert was dealing with spaces for human life. The first three were dealing with objects, physical objects, not space. Well, I have nothing against objects in architecture, although I think the space is more important. But it's very important also, the objects. But my question is this. Looking from the outside, from one that is not very aware of these questions, it seems that you are producing some weird forms. It's what someone from outside thinks, well, is this when Michelangelo made the design for Palazzo Te, he made a facade with very regular windows and well, very classical facade. Well, is this not a decoration goal for architecture, or is it dealing with the profound meanings of architecture? It's my hard question. Although I see that, well, sometimes the first parametric productions were for well, some forms, some geometries that has no meaning, no life meaning, I would say. Although you referred, and I noted that your preoccupation with responding to problems as ventilation, structure, and so you have this conscience that you have to solve problems, not only make good decorations, not a good decorative object. But well, I think you understood my question. It's for all of you.
No one wants to comment.
They're shy.
No one says a word.
It's a difficult question.
Maybe I can comment shortly.
You have from Aniruddha.
Yes.
Aniruddha, you want to say something?
You have to unmute.
Sorry, I had questions, but I'll wait for Shota to comment.
Okay, just very short comment. I think, well, on one side, for example, in our project, we tried to deal with heat dissipation, so it wasn't just a visual thing. But in general, I believe that this clear division between decoration and sort of core problems is not real. I don't think you can say, okay, this is decoration and this is the true meaning of architecture. It was historically and nowadays it was always interweaved, and I think it was kind of very problematic modernist viewpoint that you can actually separate these two things. I think the form and the display and the function are just some kind of frames created by people to describe certain things, but in general they exist in object together. So I wouldn't say it's possible to clearly separate, okay, we're dealing now with decoration and now we're dealing with some kind of core values.
Nice. Should I go? Yeah. I have a comment and a question for Ekin. First of all, I really like the fact that you present the paper as a pedagogical project and not specifically let's worry about architecture. I just have a simple question. If you say in the end you wanted to try and see if you could place it in a context or make it some kind of a building problem, did you guys have a discussion in the studio about what kind of representation suits the processes that the students undertook? Because I see some of them were very, very different from each other. The tool breaker, the three different categories that you had. What I'm trying to ask basically is, was there a point where you said, for these people, reading the final object through a plan or a section makes more sense, and for these people, they needed to represent as a axonometric or even just photographs of the model? Like I saw one which had a little silhouette line drawn with little stick figures on it. Some of that's really interesting to me. That's basically my question. What did you think was important for these processes in terms of representation?
Firstly, it was the master students, and they know how can they present, and they wasn't know actually how can they rule-based algorithm modeling, and they didn't know that, and they was really scared because with the rules, everything they are thinking everything with the rules, they are not experimental, and we was to try and break that because when giving the everything firstly, there was no end of the course, there was no everything, but this way it's so hard because we are giving big parts for the students. They was shocking and they are meeting the grasshopper, but we trying to small pieces. we tried to giving small pieces. And firstly, we didn't say we didn't say this is 3D printer, we will modeling and you will print that. We tried to touch the algorithm. They will touch algorithm, and after they will modeling. That was actually interesting for us after because some students they know rule-based modeling, but somebody was firstly knowing, and end of the modeling, end of the course, some students give up the experiments. They did totally different models, and some students did experiments, but they didn't exactly same model. But it was good. We broke the why they are scared. I hope I can answer. I could answer.
Yeah. It's more free than what I expected, but cool. Really nice stuff. Thank you.
I would say that we have 3 more presentations concerned with pedagogical and learning uses of digital tools in architecture, and this discussion will continue. Well, please, anyone else?
I have my third question.
Okay.
If there's no other, and I think that my question goes after the question of Franklim about aesthetics and beauty in architecture. So indeed, I agree with, I think it was Shota that made a comment on that. So we cannot separate, and it has never been separated, functionality, durability, and aesthetics or beauty in architecture. And my question also goes for Shota. I was very interested in following your reasoning through your paper. In the beginning, I also had probably a similar reaction that Franklim. Beautiful shapes, but what are they for? But then you come out with at the end, with some tiles, and then you also use those tiles in the flooring. Although the photo when you showed, my first impression was no one can ever walk on those tiles. So I was expecting you to put the tiles probably on the wall or somewhere else. So, but do you have the feeling that all this research on this natural, organic, generative design that can be indeed applied in some more probably functional way in buildings? Are you trying to do all that path coming from the shapes and the generation of the shapes, optimization of the shapes, and then applying them somewhere in real life architecture?
Thank you for the question. Well, we sincerely hope so. Currently, we kind of continue with our research on 2 paths. We started with what we call public surfaces, mainly floor tiles in the outside, in the exterior, and we also look into the facades, so kind of vertical surfaces in the outside, because the reason for that was obviously that heat dissipation seemed to be the potentially most clear advantage of this kind of shapes. So yeah, this includes lots of testing in the sense of scale. What you mentioned, the walkability of tiles, the first experiment was rather radical. So we're now looking whether by decreasing the scale, if it would be more comfortable without losing the certain advantages in heat dissipation, because you need certain radiuses for the air to circulate in order for this thing to work at all. So while the initial part was sort of testing the concept, whether it is relevant, it has potential, now we proceed with kind of more practical aspects of how to make it work.
Okay, great, thank you.
Thank you.
I think we have to finish. Yeah, it's fine.
Well, I think it's about time. Our discussion, our debates will continue. Most of the problems we are concerned here will continue. And I beg you to continue assisting to our sessions. We have... Sorry?
A quarter past 11. It will
Yes.
restart.
Okay, we will restart in, well, a quarter past 11. Short break now. Thank you very much to all. And hello, Tassos.
Sorry, quarter past or just 11, I think. We start 11, no? Or no?
It's 10 to 11. We have 20.
It's a quarter past 11. The time that starts.
Yes, we have 25 minutes this break.
Ah, okay, cool. Okay. No
25 minutes for the break. Thank you.
Okay,
Thank
cheers.
you.
Desliga o microfone aqui. Mute o teu microfone.